Hello. We're going to see how to search in a binary search tree. Let's take this example. Okay, this is the tree I'm looking at. I want to search for, let's say, the number 7. Okay, so what do I do? I start my search from the root of this tree. Okay, I come here and I see that its key is 50. But I'm searching for 7, number 7. I see 50 and I know 7 is less than 50. So where should I search for? I go to this direction, right? I know that since 7 is less than 50, it's not going to be on this direction, or this part of the tree, it's on this part of the tree because that's my property of a binary search tree, right? Every node to the left of x has key less than x, right? Okay. And every node to the right of x has key greater than x. Okay. So 7 can't be on this side, so I go to this node. I go to this node and I see that it's 7 and okay, I know 7 is there, fine. I return its value. Good. Something else. Let me search for 30. Again, I start, so I'm going to search for the number 30. I start from here, I see 50. Is 30 less than 50? Yes. So I turn left, I come here. And next thing I do is, I am in 7, right? I am in 7 and I know I am searching for number 30. And 30 is greater than 7. So I come here and I find 30. Good. Let's come to this tree. I am searching for, let's say, 25. Okay, 25 is not there in this tree, but I'm searching for 25. So I start from this node 10 and 25 has to be right, because 25 is greater than 10. So I come here and I see 20 and I know that, okay, so now I'm here, 25 is greater than 20, so I know I have to search on the right. So I come here and I see 30, but I'm searching for 25, so I know it has to be here. Oh, but there's nothing, there's no node less than 30, so I return no. 25 is not there in this tree. Okay, so the search has failed. This word is not there in the dictionary, right? Okay, what about 15? I search from here, 10, it's 15 is greater than 10, so I come to the right and I see 20 and therefore 15 has to be, I have to go left. I turn left and I come, oh, I reach 15, it's good, it's working. Let me now write the function for this, the algorithm for this, doing this search, right? Okay. Okay, so it's a binary search. So I'm call it, okay, let me just call it search. So it's so, and a search starts from the root node and a value key, right? So okay, now what do I do? If key is, what do I do? Okay, first of all, I'm going to return, if t is null, I'm going to return, because that's what my base case is going to be. If t is equal to null, I'm going to return false, meaning the word is not there, so in this dictionary, or this number is not there in this dictionary. Okay, so this is bool is the return. Okay, I'm just returning whether the word is there in this tree or not. That's my search. You could have returned a value if you had wanted, an integer or string, whatever the value is, you could have returned that. Okay, I'll just keep it to bool. Okay, so if t is null, I'm going to return false. On the other hand, so if t is not null, what is it I need to check? I have to check whether t dot key, okay, this is equal to, right, the t dot key is equal to this key. If, what should I do in this case? Oh, I have found out, right? So I have to return true. Right? Okay. Now It's neither of this. Okay, so now I have to decide whether to go left or whether to go right. Okay, what should I do if t dot key is less than key? Okay, that means this key which is passed is greater than t dot key. In that case, what should I do? I have to turn right. So what do? I use recursion, right? This is what we have always think recursion. So I'm going to use recursion. So for most of the tree problems, think recursion. Okay. So t dot key is less than key. What should I do? I have to search on the right and then return the value which it returns. So I'm going to write return search return. I'm going to call search with t dot right and passing the key value key. Okay. Now next thing is the key is less. Okay. Then I go left. Okay, this is what it's going to look like, and this is good, right? Okay, so this is our. You want to look at an example? So you have seen the example, and now you have the algorithm here. You can try this. Write a binary search tree, create a binary search tree, and do the search and see whether things are working fine, right? Okay, so this is an exercise. Take a bunch of numbers, take some bunch of numbers, and then try to create a binary search tree out of that. Okay, we will just now. I will right now. I will show you. I will tell you how to create a binary search tree given a bunch of numbers. Okay. Okay, we will do that now. Okay, so this is how you search for a number in a binary search tree. Good. Why is this a good thing? Why is searching for numbers in a binary search tree faster than, if you had searched all the numbers, right? If you maintain a binary search tree, why is searching faster? That's a question which we will have to address now. Okay, let's first address that, and then we will see how to insert numbers into a binary search tree. Okay. Let me just create a binary search tree, and then we will see how fast searching is. Okay. Okay, this is the binary search tree. Okay, you can verify this fact because what I've tried to do is I have tried to ensure that the properties of the binary search tree, the key values, it's preserved. That is, if I'm in this particular node, all its left children are going to be less than 80. Is it true? It's true. And all its right children are going to be greater than 80. It's true. And this is true for every node. Okay. And okay, so now I'm going to search for, let's say, a number like just pick a number 47, right? If I'm going to search for a number 47, how many nodes did I visit? So I'm going to start from here. How many nodes did I visit if I'm searching for node 47? So I start from here 50, I realize 47 is less than 50, I go here. 47 is greater than 40, I come here. 45 is greater than 47. Sorry, 45 is less than 47, so I come here and I see that it's 47. So how many nodes? 1, 2, 3, 4, right? So I see 4 nodes. Okay. What is 4 on the height of this binary tree? 4 is basically h plus 1, right? If height is h, height of this node is 3, and the number of nodes I visited is h plus 1. So now, is that clear? At least this is true for when I search for this number 47. The number of nodes visited is equal to height plus 1, right? Is this good? That's what first we are going to address. Imagine that we don't have a tree, okay? We just have some list of numbers, so let's say we have an array of numbers. Okay, the same numbers, I have it in a list, in an array. So I have these numbers in some order, let's say 50, 40, 60, and I have everything here, okay. This is a list of numbers, these same numbers, and I am searching for a number, let's say 60 in this. Now, how do you do the search? We have to do what is called as a linear search. So this is called as a linear search. Right? If you have an array of numbers and I want to search for a number in that array, all I can do is I start from here 1, 2, 3, 4. I keep on doing this, going. I will have to look at all the entries of the array to decide whether a number is there. If the number is there, if I find it in the beginning, okay, good, that's fine. But if maybe the number is the last number, so in that case I have to go through the entire list, right? So in the worst case, how many numbers should I check in an array? Okay, so if there are n elements, I have to check for n numbers, right? For example, if the number is not in the list, I will have to check for n numbers in the list before I decide, okay, this number is not in this list, right? On the other hand, if a number is not there in this binary search tree, how many searches do I have to do? Again, I have to do only h plus 1 search. Let's say I'm searching for 65. What happens? 50. 65 is greater, come here. 80, 65 is lesser, come here. 70, 65 is lesser, come here. It's greater than 60, go there. Okay, there's nothing there. So 65 is not there in this list. How many numbers did I search? 4, right? Again, h plus 1, right? So in a binary search tree, I have to do only h plus 1 search. On the other hand, if I had these many numbers, I will have to do n searches in a linear search. And what is this n? This is a complete binary tree, and what is this then n compared to h plus 1? We have the formula, right? We know what is the formula for this. And let me write n is equal to 2 raised to h plus 1 minus 1. Okay. So in the worst case, if I have to do this linear search in an array, I have to do this many searches, 2 raised to h plus 1 minus 1. But if I had binary search tree, I had to do only h plus 1 search. Now, so I claim this is good. So I claim that this binary search is better than this linear search. You all will agree that, okay, this is better because this is only h plus 1, this is 2 raised to h plus 1 minus 1. But I am going to claim the following. It is far, far better. This is a very, very, I mean, it makes a huge difference compared to this. This is my claim. It's incredibly better than, faster than this. Why am I saying that? Okay. To do that, I am saying n is equal to 2 raised to h plus 1 minus 1 is searching for these many numbers it takes far too much time compared to this. This is my claim. And let's see why I am saying this. Let's do that. Okay. So my claim is the following, that n is equal to 2 raised to h plus 1 minus 1 is much bigger than h plus 1. And yeah, let's see that. Why do I say that? Okay, so to see that, you just have to draw the graphs for 2 raised to h plus 1 minus 1 and h plus 1. Okay, so I have drawn the two graphs for 2 raised to h and h. So the point I am trying to make is that 2 raised to h is growing very fast compared to h. And this gap is it's increasing very fast. So this is an exponential function and this is a linear function. And this is expanding very fast. So the growth is very much bigger for 2 raised to h compared to h. And it has its consequences. What is the consequence? Imagine that this n is, so let's say h is, just take a look. What happens when h is 10? Okay, how many, so if you are doing a binary search tree, you had to kind of look for 11 numbers. You will have to search 11 numbers, right? On the other hand, in this linear search, what did you do? You had to search for 2 raised to 11 minus 1. 2 raised to 11 comes out to be around something like 2 into around 2000. So in this case, n becomes approximately 2000. So you can see the, so when, if you are using binary search tree, you had to search only 10 numbers. On the other end, you have to search for around 2000 numbers. Let's see, I increase further. What about if it is 20? H is 20. Right, this is now getting really big. And so what is this? So this is, so 2 raised to 10 is around 1000 and 2 raised to 20 is around 1000 raised to 2. So 2 raised to 20 is equal to 2 raised to 10 raised to 2, right? And 2 raised to 10 is 1000, so this is 1000 square. So you have something like 10 raised to 6 approximately. So this is h and this is n is equal to 10 raised to 6. Okay, but I can do it, you see how fast it's growing. H is 10 and this is n is 2000. Here h is 20 and n has already become 10 raised to 6. What about h is 30? Right, so this becomes 10 cube in that case. Okay, and this is then 10 raised to 9, huge number. Okay, good. And once h becomes 50, for example, that means when h becomes 50, this number n is so huge that no computer can ever stop running it. So no computer can go through 2 raised to 50 numbers. It's probably close to the number of particles in the universe and things like that. It's reaching that limit, and once you reach n raised to h is equal to 100, 2 raised to 100, this is a huge number, and like I mean, the number of particles in the universe, etc., I mean, are lesser than this number. So even if a computer is going to spend that much time running, it's not going to stop even after the Earth dies. Okay. Right. So that's I mean, it's that big a number. Therefore, you don't want this 2 raised to h, right? So this is a h plus 1 is a far better number than 2 raised to h. That's the main point I was trying to make. So this is why this binary search tree is far better than the linear search we saw. Okay, so BST is better than linear search. Okay, now right, next thing we are interested in is, okay, so we saw the search thing, and one another issue. We are looking at a complete binary tree. So I mean, so our answer is very good because we are looking at a complete binary tree. What if our binary search tree is not a complete tree, right? In that case, is it good? Right. Let's see that. Okay. No, I'm going to create. So this is kind of the best case binary search tree, where it's a complete binary search tree, and therefore the number of I mean the number of searches you need to do is log to the number of nodes in this tree. Now I'm going to go to, so this is kind of the best case scenario, and let me go and look at the worst case scenario now. The worst case scenario, here is my worst case scenario, tree. So there is no right node for any of the nodes, there are only left children. So 50, 30, 20, 10, 5. It's clearly, it's a path. This tree is a path, right? We saw this word. So this is a path, and this do not have right children. So now if I want to search for, let's say, 2, the number, let's say I want to search for the number 10. What do? I come here, okay, I have to turn left, 30, 10 is less, I turn left, 20, 10 is less, I go there, and there you go, I found out. What if I have to search for the number 1? I come here, okay, I go there, and I find that this is the last node, so the number 1 is not present in the tree. And how many nodes did I visit to do the search? Again, it's h plus 1, right? Number of nodes I visited is h plus 1. But what is h plus 1 in this graph? It's the same as n, right? So the number of nodes and the number of the height is the same, and therefore I mean, there's no advantage if my graph, my binary search tree is this. There's no advantage. Okay, there's no advantage to using this tree, right? I might as well have used the linear search algorithm. I could have just kept an array and I could have just searched there, and that's much better for me because I didn't have to make implement this tree. I didn't have to write this program for implementing tree and doing the search function, etc. I could have just used an array and done this check. So I should gain something of using binary search, right? That is what is missing if my tree is like this. Okay. And does this happen that if these are the numbers, the tree is always going to be like this? No. That's wrong. I can have a better tree. For example, I could have had the tree like this, 20, 10, 5, right? Okay. So this is a for a smaller tree. It has the same numbers, but it's arranged differently. So here, if I am searching here, yeah. So this is of lesser height. Okay, this is of height 2. So I can my tree. It all depends. It does not depend on the numbers I have in the tree, but it all depends on how this tree is organized. Okay, so if the tree was organized in this fashion and it's a path fashion, okay, your binary search is not effective. But if it was organized in this fashion, um, it is effective. So I could have made this into a complete tree. Let's say this is 15 and this is 25, and what I wanted was, and in the worst case scenario, this will be 30 and 25 here, and 20, 15, 15, 10 and a 5 there. Okay, so this is the worst case in the linear search. Our tree is in this fashion as a path, and it's not good, right? So this is going to take me 8 steps, 3, 4, 5, 6, 7, sorry, 7 steps. And here I would take only log 7, around approximately log 7, or 1, 2, 2. My number of searches is going to be 2 here or 7 here, right? Now, so you see what I'm talking about. It all depends on the kind of tree I'm looking at, right? So therefore, now next question which we didn't address till now is, how do I create a binary search tree? So when I have a list of numbers and I want to create a binary search tree out of it, how do I do that? And here, this is the main important point, right? If I get a tree like this, it's not useful, but if I get a tree like this, it's useful for the search. That's the main point which we are interested in. So first I will give you how to create a binary search tree, and we will notice that no, it is not good in the sense that it can create trees like this. Okay, so my how to create a binary search tree, my algorithm is going to, it might create trees like this, which is not good for us, but it will also create trees like this in some cases, which is then it's good for us. But I can't guarantee that. That's what we will be seeing. Thanks.